Okay, so we're going to start a new module today. In this module, it's just basically an extension of module 3. We're just going to look at some applications of tail bounds, particularly from an algorithmic and computer science point of view. The first one is estimating a parameter. So let me give ourselves some context. So we've looked at all of these inequalities. We want to look at the following problem. So what is given? You're given a population of n people. So think of the country like India or something like that. See, and you're given two small constants epsilon and delta, and you want to find the fraction of the people who like something, say nutty chocolates. Okay. So more practically, it will be used to estimate, for example, the people who want to vote for or against a certain policy or something. And what is this epsilon and delta? They are specifying the accuracy with which you want to estimate this parameter p. So, in particular, you want an epsilon delta approximation of the parameter p. What is an epsilon delta approximation? It's basically an interval given by some p tilde minus epsilon to p tilde plus epsilon. So, the epsilon is the error term, and what role does delta play? It 1 minus delta is often called the confidence interval. Your estimation should be correct with probability at least 1 minus delta. Another way of stating that is that your estimation can be incorrect with probability at most delta. Okay. So, that is the way I have stated it in this particular case. Okay. So, is everybody clear about this problem statement? Because very simple problem. You just need to estimate the fraction of the people who like something. And the nice thing is, the algorithm we are going to consider for this case is extremely simple. We are just going to run a for loop n times, and each time we are going to sample someone uniformly at random and independently and ask them, do you like nutty chocolates or not? If they like nutty chocolates, we are going to increment a counter, otherwise we do not. So, then what we do, we basically estimate p tilde, we estimate p and denote that estimate by p tilde as just simply x over n after we have iterated through some small n number of samples. So, the algorithm is very straightforward. The only question that we need to worry about is what should the value of n be, because obviously if you just sample one person, you are not going to get an accurate estimation, and if you are going to sample all the uppercase n number of people, that is not very useful either. That is too difficult. So, the population of India is what, some 1.6 billion? No, 1.3 some billion, I think. Okay. So, the question is, we have let's play with our intuition a little bit. Let's consider two countries, India and Sri Lanka. I mean, we've been having cricket matches recently, and we've been doing pretty well. So, feels good. We have 1.324 billion people, and Sri Lanka has 21 million people. How does this n change between the two countries? That will be an interesting question to ask, right? So, out of curiosity, what proportion, how much more samples do you need for India? But a common intuition is that, okay, so a country like India needs a lot more effort to get estimates right. So, let's see what happens. So, here going back to the algorithm, your x is the total number of people who said they like nutty chocolates, right. So, x is a random variable here, because that depends on p, which is a random variable. Why? Because the population is fixed. There are uppercase n number of people, but what we do, the randomness comes from the fact that we are sampling from this population. Okay, and this p tilde represents the fraction of the people in the sample who liked nutty chocolates. Okay. So, and x, so basically we remember we calculated p tilde to be nothing but x over n, and that we are just rewriting it this way here. However, what is the expectation of x? This is a well defined quantity even though we do not know p, p is a fixed parameter, it is an exact fraction of the number of people in say India who like nutty chocolates. So, this p is a fixed quantity. So, the expectation of x is also a fixed quantity. Okay, we do not know it, but it is fixed. In this algorithm, what are the ways in which things can go wrong? Again, once again we need to figure out what the bad events are, okay, and make sure that the bad events happen with low probability. One, remember our estimation is in the we are going to give the range p tilde minus epsilon to p tilde plus epsilon. So, anything below or above that range is bad, okay, and this is actual p value being less than the left end of the bound, and this is the p value being to the right of the bound. Okay. These are the two ways in which things can go wrong. Okay. So, let us try to formally state these two bad events. Again, if the pattern I hope you are seeing is repeating itself here. You are clearly specifying what the bad event, and you are trying to capture that bad event in a way that can be fit into a known tail bound. Okay. So, here what is, how do we define this bad event? Well, let us start with x. Okay. X we know is n p tilde, that is that we know, and another way of getting this, now you just take this equation p greater than, or inequality rather, p minus epsilon, and you multiply throughout by n. Okay. And here you have the n p tilde term. So, you isolate the n p tilde term be less than here. Okay. You isolate the n p tilde term, and so on the right hand side you will get n p, and this term will go here, plus n epsilon. Okay. So, that is what you get over there. All right. So, now you can, in this you can take out n p. So, you will get 1 plus epsilon by p, but n p of course is nothing but E of x, expectation of x, times 1 plus epsilon by p. Okay. So, this ultimately what is your bad event written in the form that can be captured by Chernoff bounds, x greater than expectation of x times 1 plus epsilon by p. Remember, that is the way in which you want Chernoff bounds, x greater than some 1 plus delta times mu. So, you notice that we have gotten exactly the form that we. The same thing can be done with the other bad event as well. Okay. You will again get x to be less than some 1 minus delta times the expectation of x. Okay. All of this is basically taking the bad event and rephrasing it in a manner that it can, where such that it can be plugged into the Chernoff bounds. Okay. So, then we can do that. So, our analysis basically is the following: what is the probability that either one of the bad events occur? Okay. There are two bad events that we listed, at least one of them should occur. What is the probability? Well, that is equal to the union of the two probabilities. The two probabilities are shown in red over here. Okay. And in the previous slide, we worked out a formal way in which we can express those bad events in a manner amenable to Chernoff bounds. So, that is what is written over here, these two things. Okay. And now this is the union of two bad events, and if you recall the union bound, if you have the union of two bad events, that is at most the sum of the individual probabilities of those bad events. Okay. And so now you can simply apply a Chernoff bounds. In the first one, it's let's see, here you have mu, and this plays the role of delta. Just to be clear, this delta is different from the delta we are using in this segment. This is the delta coming from the way we stated Chernoff bound. So apologies for reusing the same delta. So then if you recall the Chernoff bound, so what does it say? Probability x greater than 1 plus delta times mu is less than or equal to e to the minus mu delta square by 3. If you recall, this was one Chernoff bounds, and that's what is showing up over here, for instance. So here it's 1 plus delta, you have the 1 plus epsilon by p. So instead of so here oh yeah, I'm just trying to see why that happened. Yeah, you're right. So let's make sure that we're not missing something. Yeah, I think there is some typo here. Yeah, so epsilon squared by yeah, that's right. So this epsilon squared. Here also there will be an epsilon squared. The p term, there will be a p squared at the bottom, but there will be a p at the top as well. So one of the p's will get cancelled. So I missed the square over here. So the square will continue to play a role. So this is square over here. Okay. So this is just I'm approximating, instead of dividing by 2p in the exponent, I'm just if you divide by 3p, you only get a larger bound. So since we just want an upper bound, I'm just calling these two individual terms as 2 times e to the minus n epsilon square by 3p. Okay. And recall that we want to make sure that this probability is at most delta. Remember, this is one of the input parameters. The probability that we will get into a bad event should be at most a delta. Okay. So that's where this delta shows up. Okay. So now let's try to work with this inequality. So here, if you take the log on both sides, so first let's take the 2 to the other side. It's delta by 2. Okay. And then let's also do one more thing to get rid of the negation. Let's make this, let me write it over here. So what can we do about this? I can say e to the n epsilon squared by 3p should be greater than or equal to 2 by delta. Okay, I am just taking the reciprocal on both sides. Now I can take the log on both sides rather. So then what I will get is n. I will get an epsilon squared by 3p. So what I'm going to do is just I'm going to take the epsilon squared by 3p to the other side. So I'm going to make that 3p by epsilon squared, and there will be a ln over here. Okay. This is what we get over here. Okay. And that gives us, how do we interpret this? What does this even mean? It just means that as long as our n value is at least this much, we are fine. But there is one pesky issue. There is this p showing up. P is really what we want to estimate, but there is a p showing up there. What do we do with that? Yeah, exactly. So, you just want a large enough value of n. So, simply get rid of the p, and you are still going to your value of n is going to continue to be sufficiently large, right. So, basically at the end of the day, if you want to look at it, what you have is you've gotten rid of the p here. What you have here is a sufficient bound on n to ensure that you're going to get an epsilon delta approximation. There's of course this typo. Which brings us to the issue that we talked about. If you look at this, Bharat's intuition was correct. What is the surprising fact over here? There is no occurrence of capital N, which means that whether you are working in Sri Lanka or in India, the capital N doesn't occur in this bound. So, it's only going to, your estimation is only going to depend on epsilon and delta, not on n. So, that is a fairly often a surprising fact, because you are what you may fail to realize is that regardless of the size of the population, your algorithm now focus is just based on just sampling, and each time you are going to sample with certain probability p, right. You are going to get someone who likes nutty chocolates with some probability p. That does not change based on whether it is Sri Lanka or India. Okay. That's the intuition that's going on here. That is correct. So, you are absolutely right. In fact, that does bring me to the conclusion slide, where I'm want to emphasize that it really heavily depends on the fact that we are doing uniformly at random and independent samples. And as you can tell from recent past, predictions go wrong all the time, right. And we can also take a leaf from Niels Bohr's book and say, look, prediction is very difficult, especially if it's about the future, right. So, yeah, sometimes when your memory, as you start getting older, your memory becomes bad, and even the prediction about the past is becoming difficult. So, with that we conclude this segment. So, next again we are going to see one more simple application of Chernoff bound, and we will conclude with that. Thank you.